Our next notion is what do we mean when we say the limit of a sequence? Well, remember, a sequence is a function. So now we're talking about the limit of a function. Now, one of the things about sequences is since the domain is a set of natural numbers rather than the set of real numbers, there are differences in how we can approach them. One of the things that is particularly a little bit different is the graph. A function has a graph. So let's consider. If we write this function, f of x equals 1 over, let's say 1 over x squared. Well, we know what the graph of that function looks like, and let's assume that x is bigger than 0. Let's just assume for now x is bigger than 0. Well, the graph of that function, how would you find that? If you didn't know that, you would take if x is 1, the function value is 1, and then if x is 2, it's 1/4, and then 1/9, and then 1/16. And if x is 1/2, the function value is 4. And you would be able, if you plotted those, that you would play connect the dots, and you would say this is the graph of that function. And we know this function is continuous, it's differentiable, has all these properties that we play with in the original calculus, or in the differential calculus. But now when we talk about a sub n is equal to 1 over n squared, now what do we mean? Again, we don't need to write n bigger than 0 because n is already presumed or assumed to be bigger than 0. And so now the question is, what are the terms of this? When we write, when n is 1, this is 1 over 1. When n is 2, this is 1 over 4, 1 over 9, 1 over 16, and so on. These are called the terms of the sequence. The terms of the sequence are the domain values, strictly speaking. And look, we may plot these. We may plot these values. I want to graph both of these functions on the same graph. Because 1 over 1 is 1. It is, and there's 1 over 1. There's 1/4. There's 1/9. There's 1/16. We do not include the fractional values because the fractions are not in the domain. We do not include the values in between. You don't play connect the dots with the sequence because there are no values in between 1 and 2 in the natural numbers. So if you were to plot only the graph of the sequence, all you would get is, and the word is, a sequence of points. Discrete points. This is not continuous. You may not take the derivative. You may not use L'Hopital's rule. If you can't take the derivative, then you certainly can't use L'Hopital's rule. And so for sequences, a lot of the basic ideas of the calculus, of the differential calculus, don't apply. However, we can very often leverage what we know about the derivative, the differential calculus, and use that to gain information about how these computations are done. In particular, notice in this case, for all natural number values, for all values 1, 2, 3, 4, 5, for all the natural number values, this function and this function equal each other. If these functions are equal for all values of n, and they are, in fact, that's how we got this curve in the first place. So the white curve and the orange dots, if they coincide at all of these values, then the word we use, this is the sequence, and this is what we call the associated, it's the associated continuous function. I'm just going to call it the associated function. So if an is 1 over n squared, then f of x is 1 over x squared is the associated function. Not all sequences have such an associated function for the work that we're going to do. It's more subtle than that. But if such a function exists, then it's called the associated function. And it turns out that there are properties they share. And we'll talk about some of those things in just a bit. One of the things that functions and sequences and associated functions share is the notion of a limit. Now, think about this. If an is equal to, let's just pick something nice and easy here. It's 1 over n, just something fairly straightforward. It should make sense that this notion, pick a number in the domain, pick a number, let's say 5. I'm just picking 5 out of the blue. It'll work with any value in the domain. This has no meaning. This has no meaning because this means as n gets very, very close to 5. But the problem is, here's 5. The closest you can get to 5 is either, if this is what you're trying to get close to, the closest you can get is either 4 or 6. You cannot get any closer. And so this notion of a limit doesn't have any, it doesn't convey any information. These concepts are not compatible. But there's one limit we can use with sequences. We can do this. The limit as n goes to infinity. This now makes sense because what we mean here is, remember, x is not approaching infinity, although that's the terminology we say. What we really should say is as n increases without any boundary, as n gets larger and larger, as n recedes out the x-axis. Well, that's the same notion as this. If this is 1 over n, so if I need the limit as n goes to infinity of 1 over n, this is the same notion as that. Now, what do we mean by this notion? Remember, n going to infinity, this is the calculus language of a horizontal asymptote. That's a key notion. As n goes to infinity of a function, we're talking about, is there a horizontal asymptote as you go out to the right? In this particular case, we know this limit is 0. And so yes, this function approaches the horizontal asymptote of 0 as x recedes out the x-axis. We know that because we know the graph of that function. That is what we're talking about when we write those symbols. This means precisely the same thing, except that the curve does not approach the horizontal asymptote because there is no curve. What approaches the horizontal asymptote are the individual points. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. So yes, these are approaching the horizontal asymptote, just like this curve is approaching a horizontal asymptote. So these two notions share very much in common. In fact, we're going to see that one way to investigate this behavior is to first investigate this behavior. If, big if you can establish this behavior, it turns out you get this for free. Establishing this behavior, you get to use all the tools we've developed so far in the calculus. That's what I mean when I say we use, even though the derivatives don't apply here, we can use the derivatives and the associated functions as a lever to get to the behavior of this. All right? Now, for some more specific details, now, I'm not going to be asking you to develop this. This is not what you're going to need to be able to generate. But for the record, just so you see the official version, when we write the limit as x approaches infinity of f of x is equal to L, here's what that means in terms of the picture. If this is L, if a function, this is a continuous function, if x goes to infinity, f of x is equal to L, what we mean is the curve, it might be doing anything in here, but the curve eventually approaches the asymptote. And so when we write the limit as n goes to infinity of an is equal to L, we mean the same thing. We mean, here's L. Now, the terms in here can be doing whatever they want to do, just like the function in here can do whatever it wants to do. But eventually, this curve settles down and approaches the asymptote. This is one possibility. And so eventually, these terms settle down and approach the asymptote. This is one possibility. It's not the only one. Now, so what we mean is this. Given any epsilon, let me take a green epsilon. Given any epsilon, Let me make a better picture than this. Given any epsilon, no matter how small, so this is epsilon, this is epsilon, this is L plus or minus epsilon, it establishes a boundary. And what we mean when we write this, what we mean is this function gets inside the epsilon sleeve. Think of this as a long sleeve shirt that's being on the outside of someone's arm. The asymptote is the arm, and the epsilon values are the sleeve. Eventually, this gets inside the sleeve and never leaves. And that's true for every possible choice of epsilon. Even if we choose a tiny, tiny epsilon value, eventually, now you may have to go out very far, eventually this curve gets inside of there and it never leaves. That is precisely what we mean here. Given any epsilon sleeve, what we mean, if the limit of n goes to infinity, if that actually does equal L, then what that means is these points eventually get inside of here and they never get outside of that sleeve. And that must be true even if the epsilon is chosen to be very small. Now you may have to go out quite a bit further, but eventually all of these points get inside that sleeve, no matter how small the epsilon we choose. Now to make that official writing, and again, I am not going to expect you to do this. I need to leave something for you to do in your advanced calculus course when you get to be junior, senior level math majors like you're supposed to. What we mean is this. For any epsilon bigger than 0. Now, if any of you have worked through the delta epsilon proof from back in Calculus 1, this is a distant cousin to that notion. For any epsilon greater than 0, there exists an m greater than 0 such that, and this is the statement that's required, an minus L less than epsilon implies, the other way around, such that n greater than f capital M implies absolute an minus L is less than epsilon, which looks like a bunch of symbols, but it means something very straightforward. It's just what I said. No matter what size epsilon you pick, there is a point beyond which, so in this case, in the first case, this was my m. M was this number. But when you choose a small epsilon, m is this number. So the choice of m depends on how tight the sleeve was. So, but for any epsilon, there will exist an m, a point beyond which, and this is the fancy schmancy way of saying beyond that point, for all the points beyond, anything beyond m, that's what this means, an minus L, what this means is the point is inside the epsilon sleeve. And extremely unofficial, what it means is these points actually get inside of here and they never leave. That's what it means. That's what this actually means, strictly speaking and technically. We are not going to do work with this. Again, I'll leave this for you to take when you take an advanced calculus or a real analysis course. All right? But what we can say is this. This behavior is true whenever it's also true of the continuous curve. So this behavior is true whenever it's true of the continuous. And so one way to get around this is as follows. If, this is a big deal, if f of x is the associated function for the sequence AN. That is to say, they agree at every point. Then, if the limit as n goes to infinity of f of x is equal to L, we also have the limit as n goes to infinity. I'm sorry, this needs to be x. Limit as x goes to infinity of f of x, it goes to L. So if the limit of the associated function is L, then we have the limit of the sequence itself must also equal L. It says if the entire curve goes to L, then the little points that are piggybacking along that curve must also go to the same limit. So to show that a sequence converges, one of the ways to do that is to take the associated function, show the limit of the associated function converges, and if you do that, then you get this for free. And when you do this, you get to use all of your tools from differential calculus, derivatives, and if L'Hopital's rule helps, that's wonderful too. So this is one of the ways to establish the convergence of a sequence, is by showing the convergence of the associated function. So that's one way to make that happen. All right. Now, here's another way to discuss what happens with the sequence if the limit exists. By the way, here's a piece of terminology. A sequence converges if the limit as n goes to infinity of AN. A sequence AN converges if the limit of that sequence is equal to L for a where L is a finite number. If the limit is a finite number, then the sequence converges. If that is not true, then we say the sequence diverges. If not, then we say diverges. So it converges if the limit is finite. It diverges if that is not true. Now, there are a couple ways for it not to be finite. One possibility, if the limit is either positive or negative infinity, then it diverges. If the limit simply does not exist for any reason. If for any reason the limit does not exist, then we say it diverges. In Missouri, we say diverges. So if you say diverge, I know what that means because I speak Missouri. But diverges if either is infinite or does not exist. We say it converges if that limit is a finite number. Now remember what this means in terms of the picture. In terms of the picture, what this means is the terms, or let's say the graph is a better way of saying it. The graph approaches a horizontal asymptote. So if the graph approaches a horizontal asymptote, in fact, this is if and only if. The graph approaches a horizontal asymptote if and only if the sequence converges. These are the same. So if the graph does not approach a horizontal asymptote for any reason, then we say the sequence diverges. So the sequence converges if the terms approach a horizontal asymptote. A sequence converges if the limit exists. A sequence converges if the limit exists. A sequence converges if the limit exists. Because later on we're going to talk about a series. A series can either converge or diverge. Same word, but different definitions. That's the key notion. So a sequence converges if the limit exists. A sequence converges if the limit exists. All right? A sequence diverges if the limit doesn't exist for any reason. right? Now, what we're going to do is develop some tools for figuring out how to show that a sequence, in fact, point of fact, actually does converge. So we'll talk about that with our next bit of work.